from break, and this is Mr. Arnold coming at you for the STEM class. Today we're going to talk about waves. So something a little bit different today. There is an attached worksheet. If you will open that up, maybe push pause right now, go back, open up that worksheet, and you can answer these questions while I talk, and that will make it go a lot quicker. I'll try to keep it short, but you know me, blah, 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 blah. So let's just get started right now. Okay, as I said before, our chapter's on waves. And so a lot of things we have to know about waves. Most of this is just interesting. We're not going to do a bunch of math with this. We're just going to go and talk about these different things. All right, so first of all, you want to know what a wave is. Now, if you look at the animation down there below, I've added these notes onto your Schoology and Kami, but the animations will not be there. The videos will be on there, but you have to be on that little arrow icon, the select button, to click it if you want to watch them again. This case here, we have the waves are a distribution of energy that gets transferred through matter. Now, not all kinds of waves need matter, but a mechanical wave is what needs matter. So we'll talk about that right now. Now, the medium is the thing that the wave has to transfer through. So without the crowd for the wave in the ball games, there would be no wave. Without water, there would be no wave. In outer space, there is no matter, and so there is no mechanical waves that can travel through space. All right, so there's no sound in space. Now, electromagnetic waves, if you look down here on the bottom, it says electromagnetic wave. Electromagnetic wave is another name for light. And there's all different kinds of light, not just visible light like we think, but X-rays, microwaves, gamma rays, any kind of thing you think of radiation is a type of light, an electromagnetic wave. And it doesn't need a medium. And that's why light can come from the sun and reach us from outer space. Now, to make a wave, you have to have some energy form. And that energy form has to make, in the case of a mechanical wave, the medium to vibrate. Now, there's going to be three main types of waves that we talk about in class, and these are separate from the mechanical versus the electromagnetic wave. And the first wave we'll talk about is the transverse wave. And transverse means to go across. And so transverse are going to be those waves that we think of when we think of the sine wave. Longitudinal wave is a wave, longitudinal meaning it goes with or parallel, and the waves will travel parallel to the medium. And then the surface wave, also known as a combination wave, is a combination of both transverse and longitudinal together. And then, of course, we have the friendly wave. All right, so our transverse wave, you notice our transverse wave because the object, it's going up and down, and the energy is traveling through. So think of if you're holding on to a rope or a hose, and you're moving it up and down really fast, and another person has the other side. That other person's going to feel the energy travel through the rope and get to their arm, right? And the rope itself is going to move up and down. So the medium moves perpendicular to the direction that the energy in the wave is traveling. We have parts of this wave, and these parts are probably things you know. I don't spend a lot of time. The crest is the top part, the highest point of the wave, and then the trough is the lowest part. Now, the longitudinal wave is the wave that travels in the direction of the wave. So this is like, these are like slinkies or springs, right? You push on a slinky, and it sends that wave right through that slinky, right? And so it travels in the same direction. The spring travels the same direction as the wave traveling through it. Now, one type of longitudinal wave you're really familiar with is probably sound. All right. Now, we have parts for this longitudinal wave, and those parts are called the compressions. And the compressions are where it's squeezed together. which makes sense because we know compressing things means squeezed together. And the other one is the rarefaction. Now that's not refraction, that's rarefaction. And rarefaction is where it's been stretched out, pulled apart. And you can see through that little slinky picture there. Now, sound is probably the longitudinal wave that you are most familiar with. And when this is a tuning fork there. If we were in class, we'd have these out. And it's creating energy. It's vibrating. And it could be a guitar string or whatever. And what it does is it squeezes that air together and creates those compressions. And as it squeezes together, it forces energy to travel through that wave. And that is a longitudinal wave, can also be known as a compression wave sometimes. Now, here's that combination. Now, you have to look at those little blue dots, right? And so when you think of water waves, you think of all sorts of different things. You know, most people probably just think, oh, that's a transverse wave. But if you can see the whole material and see it, look at that. It's moving in a circular pattern. So what's happening is there's both types of waves traveling at the same time. You have the compression wave or the longitudinal wave and the transverse wave interacting with the water molecules. Sometimes we call these surface waves. Sometimes we call them combination waves. All right, now, so there's 4 basic properties of waves, and these goes for both, all 3 types of waves. We have the amplitude, the wavelength, the frequency, and the speed. And they're interrelated, and there'll be more stuff on this right now. Let me go to the next picture so we can see what they look like. Okay, so when we look at here, let's zoom in on, I can't zoom in, I'm sorry. Let's look at the amplitude. So the amplitude is how far it is from the resting position. So when you talk about the amplitude of a wave, say it's that slinky like below and you make a big wave, a big hump on that thing, right? The further it is from the original position, that is the amplitude. All right? And if you're talking about a longitudinal wave, it'd be how far the molecules are compressed or how far they're stretched out, that rarefaction again. So it's how much from the resting position. All right, here's another picture here. And when we're talking about the amplitude, and most of you guys have heard of amplifiers. I have a guitar amplifier right behind me right now. I'm not going to plug it in right now, but what it does is the amplitude is how much it creates more energy for the wave. So the higher the energy, the greater the amplitude. The lower the energy, the lower the amplitude. All right? And so if you want a louder sound, you need more energy. You need something to give it that energy, and that's why we use a guitar amplifier. Wavelength. Now, this picture of a wavelength, I probably should have put a different one on there. But the wavelength, I wonder if I can pause that. Oops, I don't want to do that. Let me go back. Okay, so the wavelength, let me go to a better spot. Okay, look on this wave here that it has on top with the letters. Now, if we want to go wavelength, a wavelength's definition is from the one position on the wave to the same position on the next wave. All right, so if we start at, let's say we'll start at B, all right? So when we go through the wave, we're going to drop down, right? And then it comes back up at E. Now, that's not a wavelength. It has to be a complete wave has to travel through there. So all the way from B to G, the to and fro, the trough and the crest, complete wave would be both things. All right. So it could be any point on those waves. So if we start at B, the wavelength is from B to G. If we started at E, the wavelength would be from E to J. If we started at A, the wavelength would be from A to F. So it's the distance for the whole complete wave, and that's talking about the above the resting position, above the dotted line, and below the dotted line is one wave. Okay, frequency. Now, frequency is the waves per second. Now, we use seconds because waves are usually traveling pretty fast. Now, the amount of waves that pass per second then would be called a hertz. So if you have 1 wave per second, that's 1 hertz. If you have 10 waves per second, that's 10 hertz. And so if you're familiar with, well, let's not talk about that. So it's how many waves that pass per second. All right. Now, because of the way the wave is, and all waves travel the same speed depending on the medium they're traveling through. So if it's a sound wave, they all travel the same speed. If it's a water wave, all those waves travel the same speed. If it's a wave through a spring, it's all the same speed. Now, what makes the difference in the frequency is how many waves per second. So if you increase the frequency, and look down at the purple, that has a higher frequency, right? Then the wavelength will be shorter. If you decrease the frequency, that means fewer waves per second, then the wavelength is longer, right? They're called inverses. One gets bigger, one gets smaller. So the frequency and the wavelength are inverse relationship. Okay, now I'm going to stop on that today. And I'll have a little paper that goes with this. So make sure that you fill out that paper if you haven't already done so. If you didn't do it, it's not hard, and you can go back through and check that out. Hey, remember, you have to fill this stuff out. It counts as your attendance. Have a great day. Hey, there we go again. So I have to turn this off. Have a great day.